Hi, class. This is the final solution uh, for last week's exercise. You still have one more assignment to turn in. That's your final project. Again, I really don't want you to stress out too much about it, but I want you to have the opportunity to build and test and flex all of the skills you've learned over these past few weeks. So take your time with it. Feel free to reach out to me. And by all means, please do not stress out too much about this. You've already learned a lot in this course, and I hope it will serve you well. View this as an opportunity to cement what you already know. With that, let's go over this week's exercise. So just to recap, we were using data from an article that was published in Science that studied the effect of different incentive strategies on vaccination rates amongst individuals, I believe, in Sweden. And what they did, and one of the really great things about what they did was that they were very transparent and posted their data, as well as all of their code to use their analysis. So we're just gonna first get started. One of the little changes that I made to their data set was they did something odd with their vaccination rate. I'm not quite sure why that scaling variable was there, but for some reason things were scaled 0 to 100. But you know, we're just going to make that a dummy variable to make sense. So the first question I asked you was what percentage of individuals are vaccinated in the data set? That's just a straightforward tab command. And as we can see, roughly 73% of the population is vaccinated. The next step, I gave you this regression, which is to assess the efficacy of all 5 treatments they tried. And again, we left out this control group because that is going to be our reference group. And just for the sake of completeness, you can also do control and this argument no constant. And again, it will be your coefficient on your constant will be the same, or it will be the exact same as your control, but the interpretation of these variables change. And depending on the circumstances, you might not want to do that. So for instance, when I write the regression this way, the interpretation of my hypothesis test on the treatment variable is no longer on a treatment variable like treatment payment. It becomes, is this statistically significant from 0? And not, is it statistically significant from our constant? So note that the coefficients and the point estimates are actually quite similar in terms of meaning if we were to use the predict function. But in a scenario like this, it's much harder to tell the absolute difference across coefficients and whether or not a particular coefficient is statistically significant from, say, our control group. Now, the first thing I asked you to do was evaluate this regression where we regress vaccination status on the 5 treatment arms. And we can see from our F test that we get a score of around 2.1, and it's associated with a probability of 0.056. So in a case such as this, we would actually fail to reject the hypothesis that all of these coefficients are 0. I asked you to document which of these coefficients is largest and most significant. Sometimes that'll be the same thing. In this case, it happens to be. We saw that treatment payment, in other words, paying individuals to get vaccinated, had the largest impact. It raised vaccination rates by around 4%. And it's got an associated p-value of 0.01, suggesting it's a pretty significant effect. The next thing I ask you to do is to assess whether or not the social and behavioral treatments that's providing a patient information about vaccination, trying to persuade them, making some social appeals. This treatment min argument was declared basically the minimum treatment. That's just sending an appointment reminder. And so we can jointly test whether or not all of these coefficients are zero using this test command. And what we see is that we've got a p-value of around 0.2. So again, we failed to reject the null hypothesis that these coefficients are all zero. So another way we can say is that there's still a decent chance that the point estimates associated with these three parameters could all be zero. Next, I ask you to predict these values to generate the predicted probabilities associated with this. And one thing that I think people might have been a little bit surprised by is we only have 5 unique values for each of these predicted values. And in part, that's because the regression we're using, it only has 6 parameters that you can either be one treatment, you can only be one of the 6 treatments. So as a result, you really can't have that much variability. And we see that in this case, like most of the time, we're going to be predicting somewhere between 70 and 75% probability that you're going to be vaccinated. And let's run and do that exact same analysis, except this time we're going to use a logistic function. And all a logistic function is doing is saying that we are going to bound the predicted probabilities instead of being that they cannot take values between beyond 0 or 1, meaning you can't have negative probabilities and you can't have probabilities greater than 1. So let's run that estimate. And let's run that in comparison to linear regression as well. So we can see them side by side. Now, when we look at this third column, the t statistic and the associated p-values, for this specification, we actually get pretty similar results. That the z-scores are similar, the p-values are approximately the same, but these coefficients themselves are pretty different. And the reason why, as we talked about before, is when we run logistic regression, we're not trying to predict the individual outcomes per se. Instead, what we're modeling is the log odds of these events. And so the interpretation of these coefficients becomes a little bit trickier, and they have a nonlinear interpretation. So for instance, if we were to compute the marginal probability of, say, being assigned to the treatment group, we can see that it's roughly on the same order as what you see in the linear regression, but these coefficients aren't exactly the same. And in fact, when let's try a few different values just to see what's going on. 1, 2, and as we can see that this coefficient sort of attenuates and decreases as you keep on. This coefficient attenuates as you get further and further away from small values of treatment payment. That effectively, if we assume that treatment payment were 100, but it doesn't have any material effect on an additional, say, assignment of treatment payment. Again, this is a case where treatment payment is a binary variable. We can do the same thing with age, and I think it makes a little bit more sense there. But the takeaway is that the interpretation of the margins command varies a lot more as a function of where you are. And we saw that a little bit in terms of your covariate space. And we saw that a little bit with regards to quadratic and polynomial regression. But with logistic regression, that it's particularly true and something you need to be very cognizant of. And let's generate those predicted probabilities. And let's have our logitprob LPM. And what we can see, in fact, is that we actually generate the exact same values in this case, because we rerun a linear model and a logistic regression model, but because we actually get the exact same results. You're not always guaranteed to have this, particularly when you're modeling, say, outcomes that have continuous variables in that linear regression case, but here we do. And just to make this doubly clear, we can see that the correlation is 1 and that all of the linear probability models are identical. So one thing you might be wondering at this point is, well, how do we evaluate model fit? So with regression, we have R squared. What do we have with logistic regression? So there are different metrics, including a pseudo R squared. But the things that I tend to think about from a binary classification model is metrics like model accuracy or this ROC curve operator. As we talked about in class, that anything less than 0.5 is doing actually worse than random guessing. And so the model with 5 variables really only does incrementally better of predicting a person's classification status of being vaccinated or not. And when we graph this ROC curve, you can see that, as I mentioned before, that this sort of figure should be bowed outwards to the top left when it's doing a good job, that the curve has a lot of area under it is basically what you're looking for. And here we see perhaps only a little bit of area between that and that 45-degree line, suggesting we are in not great shape. And in fact, when we look at the classification accuracy of this tool, our prediction model effectively always says that if our cutoff is at 50%, that's this parameter here, and that's typically the default. You're always going to guess that everyone gets vaccinated. And we can see that the model is about 73% accurate, 72.85 to be exactly. It's capturing everyone who gets vaccinated. That's the sensitivity or recall number. It's failing to identify any cases in which the model predicts that an individual will not be classified as vaccinated. And this negative predictive value, it's missing because you can't divide 0 by 0. So that's the high level takeaway. We can choose different levels of cutoffs, and particularly for like medical decision making, you might decide that, well, it's more important that we identify all of the individuals who might be likely to be symptomatic, and then we might choose a lower cutoff. Whereas if, say, we're using a diagnostic test to identify folks who don't have a disease, we might choose a different cutoff. In either case, just to make this plot and table look a little bit more interesting, it shows a cutoff of 0.75. And what we see is that now we correctly identify cases of both true and true positives, false, true positives, false positives, false negatives, and true negatives. And we can see that when we choose this higher cutoff, our accuracy rate goes down. But we do actually have some specificity to our test now. Now, again, we were using a pretty simple model here, 5 dummy variables. Let's try what happens when we really throw everything we have in the covariate space out. So we're including variables for treatment status, age, gender, their civil status, their education, their occupation, their income. And we use that wild colored operator to capture all of the dummies that if you describe the data set, you can see it up there, quite a lot of them. Cool. So let's do that and see. Even with all of these features, we're actually not explaining a whole bunch of the variance. That the pseudo R squared is less than like 2.5%. And so let's just take a look at that. So even though we're not necessarily explaining a whole bunch of the variance, we can see that with this saturated model, we have an ROC curve that looks a little bit better in terms of the accuracy, the AUC trade-off. That we can choose different points with different levels of sensitivity and different levels of specificity. And we can see that particularly this distance from the vertical line or the 45-degree line is bowed outward, which suggests that the model is doing a little bit better at distinguishing and that there's a continuum of trade-offs that a researcher or a diagnostician might be interested in utilizing. Lastly, what we can do is we can also look at just classification accuracy. So we went from a model that had 72.85% accuracy to a model that has like 72.92% accuracy. So despite all of the covariates and things we've added in, we really didn't see that big of a change. We're at least predicting some cases where an individual is not likely to get vaccinated, but it's not like we had a huge increase in model performance. So this is a problem known as class imbalance, which you'll learn a lot more about if you go on to take courses in machine learning. But I just wanted to highlight that some metrics move a whole lot and other metrics do not. And the last bit, I just wanted to make sure that folks understood what treatment effects were and why they can sometimes vary. So what we do is we go through and I asked you to estimate the following regression. And we are regressing the effect of vaccination on treatment payment. And what I want you to note here is that both the treatment payment and the constant are substantially different than the model we ran previously. And what is going on here is that instead of estimating the treatment effect relative to a true control, which we're doing in this specification, when we regress vaccinated on treatment status, we're comparing the difference between paying individuals versus this pooled treatment effect of all of the treatment arms we're not including plus the true control. So what happens if we drop all of that? So if we keep only the treatment and control group, we basically recover our true or our previously estimated treatment effect and our previously estimated constant. So that is one of those big pieces of information to understand that even when you think you are getting the same estimate, you really need to pay attention to what data you're including or excluding. Now, other ways we could have done and generated this estimate, we could have done a t-test. Another question that people often like to ask about treatments is whether or not they're so-called heterogeneous treatment effects. That means, did the intervention vary by individuals? So for instance, was pain men versus women more effective? And what we find, we can run this interaction term. And as we talked about before, you want to typically include both the interactions and the individual terms. You see the coefficient here is pretty close to 0, and it's got a huge p-value. So with that in mind, we can safely say we fail to reject heterogeneous treatment effects in this intervention. With that, we are done. Thank you all so much, and I look forward to reading your write-ups. Take care.